Okay, so today we're going to talk about the conceptual understanding of polynomial division, and we are going to start with an example like 288 divided by 12, and we're going to do it in the long division way, which means we're going to start with 12 on the outside, and that's going to go into 288, and of course we're going to solve it the traditional way by saying, okay, how many 12s go into 2, which really is really not 2, it's actually 200, but 12 doesn't go into 2, so we ask the question, how many 12s go into 28, which is really 28 tens, but we still can ask the question anyways, and we say that 2 of those, I need two tens of those, really is what I'm saying, and that gives us 24 or 24 tens. We take that away. We have 4 tens left over. We bring that 8 down, because we want to continue going, and we have 48, which is really 48 ones, and we ask the question again, how many 12s go into 48? And that would be, we need 4 ones of that to go into 48. So we put that there, we subtract down, and we see we have a 0 remainder. So the quotient of 288 divided by 12 is 24. Now we can look at this in a little bit different way. Like I was saying, 288 is not a number that means 280 or 8 tens plus 8 more ones. And I'm going to switch colors here, and we can go and we could actually rewrite this as 12 divided by 2 hundreds plus 8 tens plus 8 ones, like that. We could also write it, if we want to be a little fancy, we could write it as 2 times 10 squared plus 8 times 10 to the first power plus 8 times 10 to the 0 power, or we can just leave it as times 1 here. All right, and if we want to go through and we can actually go and find that 24 again, we ask the question, well, how many 12s go into 200s? But since this is 12, actually 12 ones, not 12 hundreds or even 12 tens, it's 12 ones, we need to figure out a little bit different. So 12, of course, does go into 200, but not as nicely as if we were to put it together with the 8 tens. So we can actually rewrite this as 28 tens and re-ask the question that way. How many 12s go into 28 tens? And we can see that, indeed, I need 20 of those. Let me back that up to a second. I need 20 tens, which would give me 224 or 240, 24 tens. And when I subtract and leave what's left over are 4 tens, which matches up with the 40 in the 48 above. Okay, I bring down the 8 ones, and now I've got 4 tens. Of course, 12 ones does go into 4 tens, but not as nicely as if I were to rename the 4 tens and 8 ones as 48 ones. And so then I can ask the question, how many 12 ones go into 48 ones? And that, of course, is 4 ones. Okay, which I put up on top there as 4 ones. And we get 48 ones again. And since the two numbers are identical, when we subtract, we're going to get a 0 remainder. So this seems a little more complicated than doing long division the traditional way, but this is exactly what we're doing when we do long division. And the reason I did this is because if we look at the 2 times 10 to the second power plus 8 times 10 to the first power plus 8 times 1, what we're seeing there is very similar to a polynomial. If I were to replace the n's or the tens with a variable n, you can see that it is very similar to how we write a polynomial. In fact, it's identical, except here we know what the variable is equal to. We can still call it place value, even though it is not a number we would normally associate with a place value, like we do with tens. So let's consider the polynomial division here problem. I'm going to move up a little bit, and we're going to look at this polynomial, x to the third power plus 4x squared minus 5x minus 14, and we are going to divide that by x minus 2. And now, normally that would look kind of crazy, but now that we've talked a little bit about long division, we can actually do this in a long division format. If I put x minus 2 as the divisor on the outside, and put my x minus x to the third power plus 4x squared minus 5x minus 14, put that all inside, I can ask the very same questions that I did with the 288 divided by 12. I need to know how many x minus 2's I can get out of that larger polynomial. And our quotient will end up being another polynomial with a degree a little bit less, one less than what we're starting with. And that's okay, because that's what we want. We're trying to break this polynomial up into smaller pieces, trying to figure out what its factors are going to be. Perhaps we'll use it for solving or something like that. So to do that, we need to figure out, okay, what do I need to subtract away? So, in fact, this is going to be a lot easier because we can really choose any numbers we want, that as long as they work with us. So to figure out what to subtract from, I'm going to look at, just like we did before, I can't really go into the third powers. We don't really have x minus 2 x cubes. We don't have that place value. But if we multiply by x squareds, we can get that place value, just like we did with the tens and hundreds. We multiply by the smaller place value, we can actually get a larger place value. So if I start with multiplying the x minus 2 times x squareds, and since the coefficients are just 1, I just need an x squared, a 1x squared. That makes it pretty easy. I can just multiply through, and I get x to the third minus 2x squared. And just like with whole number long division, we're going to subtract those, being careful of negative signs, of course. And the x to the x cubes are going to cancel out, go to 0, which is what we want. We don't want that anymore in our remainders here. And the 4 and the 2 will end up combining and making a 6x squared. Okay, now we move over and go to the next term. I'm going to bring the 5x down, okay, and ask the question again. Well, in this case, I'm going to move to the next place value over, which is x to the first power, okay, and our x's place value as opposed to our x squared's place value. And I need 6 of those. I need 6 x's of those in order to make them work. So I'm going to, again, multiply through, get my 6x squared, and the 6x and the minus 2 will make minus 12x. I'm going to subtract that group away as well. The 6x's will conveniently cancel again, because that's what we want. And the 5 and the 12 will combine and make a positive 7x. Now finally we want to get down to our 1's place here, which is the 14. I'll bring that all the way down, and then ask the question again, how many do I need to get out of there? Well, it turns out that I'm just going to need 7 of those. 7 times x will give me a nice 7x there, which will work fine. And, oh, look, it's going to actually work with the 2 as well. And if I subtract this away, I'm going to get 0 remainder on that, which works wonderfully. We could end up with a remainder of some kind, and then if we had to, we could actually write that as a remainder. It wouldn't go any farther. There's no decimal form of this polynomial that we could actually write like we could with whole numbers, but we certainly could, if we had a remainder, write it like a fraction. In fact, that's where mixed numbers come from in some sense, because fractions are remainders of divisions of things like that. So when we have improper fractions. So I'm going to move up and just kind of rewrite our answer here, write our result. I'm going to switch colors. I kind of like blue right now, so let's go with our quotient, which is going to be x squared plus 6x plus 7. And we're going to find out that that times our x minus 2 is equal to our original polynomial of x cubed plus 4x squared minus 5x minus 14. And that is one way to start factoring that larger polynomial. We could go into the 6x plus 7 next and figure out other steps with that. But there might be other ways as well. And in the next lesson, we're going to look at an even faster way to kind of divide these polynomials. So we'll save that for next time.